Hello, everyone. I'm going to revisit the kernel method today in this discussion. So first, we are going to talk a little bit more about kernel perceptron, as we discussed in the class. So first, let's revisit the perceptron algorithm. It is basically a linear classifier, right? So suppose our dataset is a binary classification dataset, and the input is from a d-dimensional space, and the labels are either -1 and +1. So this is our dataset. And our model is a linear classifier, right? We have the parameters is either, we have two parameters. First is W is other d-dimensional vector, and the B is a scalar. And our decision boundary is W multiplied X plus B equals 0. And if we want to make predictions on points, we will just use the sign of this multiplication. Like if this sign gives you like +1, then you label it as +1. If your sign gives you -1, then you label it -1. So visually, this means that for example, if we have like a set of points here, and its label is -1, and we have another set of we have another set of points here, and it's labeled +1. And the perception basically trying to find a line that separates these two clusters, right? And the line we define, we call it the decision boundary. It's Wx plus B equals 0. And if we have a new point here, and we want to make prediction, then we just check this sign Wx plus B, right? If it is above this line, then this thing should be like the next I'm not sure it's negative or positive, but it should be in this case it should be positive. Sorry, it should be positive. So I think I make a mistake. So this should be positive and this should be negative. Yeah. So this is how we make predictions on a new point. So and then we have the data, we have the model, right? And then the next problem is how can we train the classifier to learn this model, right? So remember the parameters our model has is W and B, right? And the learning problem is basically how to find the correct W and B. And we've already learned that the perceptron algorithm is basically we just keep cycling through the training data, and we found some point is already misclassified. In this case, the multiplication between your prediction and your true label is less than 1. It's less than 0 means that your prediction is incorrect, right? In this case, you just update your weight and also update your bias. So this is how you train your classifier, or how you learn this classifier. And for prediction, if you already learn if you already have the W and B, then when you make the prediction, you just follow the previous rule, right? Use this sign this to make a prediction. Okay, so this is our perceptron algorithm. So the perceptron is a very simple algorithm, basically a linear classifier, right? So it has its limitations. So it is simply not expressed enough for those complicated problems. Like, for example, this problem, it is not possible to use perceptron to perfectly separate these two clusters, right? Because perceptron is basically a linear line. Then no matter how you draw a linear line, in this case, you cannot perfectly separate these two clusters. This means that this linear like classifier is not expressive enough. And similarly for this second graph, if you have this cluster here and another cluster here, then you cannot simply draw a line to separate the two clusters, right? So this is the limitation of this perceptron algorithm in its plain form. So then we have the kernel perception. Basically, kernel perception is try to like address this low expressivity problem of the original perception algorithm. So the idea is quite simple. Basically, we just expand the features, right? So, um, so like if originally we only have like x1, x2, these two features, then we basically do some combination of them to expand it to some like higher dimensional space, right? This additional feature could be some functions of this x1 and x2 of the original features. So this is how we expand features. And we call this expanded features the phi x. It's typically in a higher dimension space than the original features x here. So then we just revisit the learning problem, right? We need to define the new learning problem and the prediction problem for this kernel perception algorithm. And it is actually quite simple. So if you see the difference between the original perception, right? This is original perception, and this is a kernel perception. The only difference is we replace the original x, all the x here, all the features here, right, with phi x, the new features. So this is what we mean by expand features. We basically replace the features with the new features that typically is in a higher dimensional space. And similarly for prediction, we are also just replace our original x features with the new features phi x. So that's it. That's how we do like this feature expansion for this kernel perception. And the benefit is, and we can do like an example, like remember like the key difference basically like we replace original feature x with a new set of features phi x, right? We can do an example for this is quadratic kernel. Like for example, if our like original features is x1, x2 up to xd, right? This is a d-dimensional space, d-dim space features, right? This is our original features. And if we want to do like expand these features to in a quadratic manner, then what we do is we of course we also include original features, right? But now we also add the like squared of these original features. So this is x1 squared, x2 squared, up to xd squared. We'll also include the multiplication between the two features, like x1, x2, x1, x3, and x1 up to x1, xd. And also we have x2, x3, x2, xd, right? Up to x2, xd. And we have xd minus 1, xd, up to xd. Yes, right. Oh, sorry. So it should be. So we'll have this many features in the new feature set. This is how we expand this like this original features in a quadratic manner. We call this quadratic kernel. So then our model is actually quite expressive in the new higher dimensional space, right? We have all the like this combinations of these features, and now we can successfully classify all these complicated problems just use the user perception. It's still linear, but it's linear in the higher dimensional space, then it won't be linear in the original space. So I'll give you a visual explanation is how it is achieved. For example, for this case, originally, if you use like only the original features, you cannot find the linear line separated these two clusters, right? But now, so for original, let's say the original features is x1, x2, right? This is x1, this is x2. We have two features. But now let's map it to a new features. Let's say this new features is x1, x2. This is original feature, right? We add a new feature. It's called x1, x2. x1 like multiplied by x2. Yeah. So this is our new feature. Then basically we are like transforming this original 2D space to a 3D space, right? Our 3D space is look like this. So this is, let's say this is x-axis. So this is original x-axis, x1, x2, And let's say this is like the new axis, x1, x2, right? x1 multiplied by x2. So then what would be the position of this these clusters in the new 3D dimensional space? We can see that, let's focus on the center of this cluster, right? This is about 2, 2, right? This is 2, 2, right? Now in the new space, this is still 2, this is still 2, right? So it's about here on the xy plane. But on the z plane, on the x1, x2 plane, it probably would be like about 4, right? About here, about 4. So then this new cluster would around here. So this is one cluster of this of the red points. What about another cluster? About cluster at the center is about at the 9, right? So, and then we find 9 here in the new space, and 9 here is probably here. And what about the new feature? The new feature would be like about 81, right? But way above this point. Let's say here. Probably let's say the new point would be something here, right? So this is our new set of points. Now we have the red points mapped to the new space. What about the black points? The black points is, let's see, that's the coordinate of the center is 2, 9, right? This is 2, this is 9. So then on this figure, it will be something here, right? Something here on the xy plane. And sorry, this is only on the xy plane, and we need to also figure out the x1, x2 plane. It will be 18, right? So it will be something here. It's probably a scale, it's probably wrong, but just for illustration, it should be fine. And it should be around here. Right, so this is our new black points. And similarly, I won't go through in detail like this set of points. Where would it be? It probably would be something here. I guess something here. So this is our new set of black points. Right. So now we've mapped all our points to the new space. Right. Now in this new space, we can actually find a linear thing. Right. In a 3D space, a linear thing is a plane. Right. A 2D plane. We can easily find a 2D plane to separate these two set of points, right? And if you map this this plane back to the original space, you will see a shape like this, right? So it's no longer linear in the original space, but it's still linear in the 3-dimensional space, in the new like expanded feature space. So that's kernel perception. Basically, we expand features to make them more expressive. We can now classify in more complicated problems. But there's one problem of kernel perception. It is very inefficient, right? At least in the original form. Let's see, remember the key difference between the kernel perception and original perception is we replace the original feature set x with the new feature set phi x, right? And we do this for all features. So then the major problem is that how much competition we need to spend on this phi x to compute this phi x, right? Let's see if this is let's still use the quadratic kernel example, right? Let's say this phi x is x1, x2, up to xd, and x1 squared, x2 squared, up to xd squared, and x1, x2, x1, x3, up to x1, xd, right? And all the way up to xd minus 1 xd, right? We have this many features. So how much computation when you spend on these many features? First, we have we need to compute each like entry in the feature set, right? So this would require D, right? There are D entries, same as the original features. And this is another D, right? This is another D. And what about this? This is basically we want to choose 2 from D, right? I guess so. We can express as a combinatorial number. D choose 2, right? So this is about the D squared, right? It's in the order of D squared. So means that Now we need to spend like d squared computation to compute this feature set. But originally, to compute the original features, we only need d, right? Original features, we only need d. So this is too bad. I mean, we cannot spend like the square time to compute these features. This is both true for learning problems because you need to compute phi x here, right? And also it's true for prediction problem. You also need to compute phi x here. So this is the computation cost is high. But we have then it comes the kernel trick. Kernel trick tells us like we can actually still do the kernel perception thing, but we actually can reduce the computation cost a lot, even similar to original cost. How can we do that? First, we convert the original learning problem to a do form. So this is the original learning problem, right? And the do form is like this. So I think you should have learned this in the perception class. But if not, you can just look up the Wikipedia or something. So basically, this is the do form of the original learning problems. And in the do form, our the weight is expressed as a linear combination of the features multiplied with the labels, right? And the algorithm is basically this is original W, right? You replace the original W with its a linear a weighting format. And when you do the update, you don't do update to the W, but you do update to alpha. Then this is how you learn the new weight, the weight. And we can also convert the prediction problems to a do form. So here it is a little bit simple. Basically, you just need to replace the weight here with its expression in the do form, right? It's kind of like it's kind of like the linear weight of the features multiplied by the labels. So then we can actually observe something interesting is all the computation related with the features. I mean, phi x, right? Features will mean phi x. The new expanded features, they are all in the form of dot product, right? So as we see in the learning problem, what we need to compute is only for the phi x. It is only like a dot product, and it is also true for the prediction problem, right? The only thing related to computation of the phi x is just its product, dot product. So then we can do something magic. So I'll claim that we can actually do the dot product without actually computing all the features. We don't need to to expand the features. This is called the kernel trick. How can we do that? So we need to let's still use quadratic kernel as example, right? So we need two steps. First is we need to tweak the original feature expansion a little bit. So suppose our original features is x1 up to xd, right? And originally how we expand the features is we add all the squared terms and also the combination of these terms up to order 2. But now let's do something, tweak this a little bit. We add a 1 here and also multiply this original features with square root 2, right? And this part is unchanged. And this part will also multiply with the square root 2. So we tweak this a little bit. And now let's see, there's something magic happens in the dot product, right? So let's say we want to compute the dot product between two sets of features. So this is the feature of x input, and this is the features of z input. And we just write this out. This is the expression of the feature set of x. This expression of the feature set of z, right? And if you actually do the dot production, you can actually find out this is equivalent to all these sum terms, right? And you can also simplify it further. You found that this actually can be grouped into just a square, right? And eventually you will find that this is all about, it's equivalent to compute this thing. I mean, you only need to compute the original dot product plus 1, then do a square. So this means that you can save a lot of computation when you're computing the dot product, right? You don't actually need to compute all the features here, right? You can directly compute the dot product, and that dot product only involves the original dot product plus 1 and s squared. So that's much computation saved. So how much? Let's make it more specific. So like for naive computation to expand all the quadratic features, then compute the dot product. What computation do we need? As we mentioned before, like the dimension of our new quadratic features would be something like I guess it's d choose 2, right? Plus d plus d. Okay, similar in this order, right? So then its time complexity would be d squared, right? Similar as we mentioned before. But now we don't need to expand all the quadratic features. If we only compute the dot product, this is only thing needed in the perception algorithm. Then we only need to compute this thing, right? And this thing is actually doable in OD time, right? Because X and Z, they're both d-dimensional, right? So you can see that we can save a lot of computation from d squared computation to d computation. So this is the kernel trick that can magically reduce your computation cost when you do kernel perception algorithm. And this is also true for other like learning algorithm like SVM. I think we also mentioned this in the class. Okay, so that's it for the kernel perception algorithm. Next, I'll mention a little bit more about the string kernels. And the string kernel is basically we want to apply perception to it happens when we apply perception to text classification. Let's say our text classification problem is we want to classify like a word to a label, right? And the label is basically whether this word is ended with T, right? And this is a binary classification problem, a typical binary classification problem. And we want to apply our perception algorithm, and our parameter is still W and V. The decision boundary is still W times X plus B equals 0, right? And how can we do the prediction? We still use the sum of this multiplication, right? So this is the same as before. But there's one thing we need to think about first when we apply the perception algorithm is how can we convert string to features, right? We cannot directly multiply W with strings, right? We need to first convert string to some numbers. And this can be done by simply by a lookup table. For example, I can map bar to 1, right? I can map bat to 2, I can map car to 3, and I can map cat to 4. So this is how I build a lookup table for the original inputs. There are 4 inputs here, right? And then I can apply the perception algorithm. But you can see that here the feature set is still like small. I mean, it's probably not expressing enough for perception to work. And then the idea comes again that we want to expand the features, right? And one idea to expand the features is we'll not only look at the strings in the whole, but we want to also look at substrings, right? We want to convert the substring to features. So basically what we will do here is for each substring, we'll define its feature as this phi sx as the number of times the substring appear in X, right? For example, if our X the string is bat, and our substring is B, right? This is our X, this is our substring. The substring is BA. Then what is phi sx? It just would be 1, right? Because BA appeared once in the original, like this bad word, right? B, this would be 1, right? What about phi, let's say BB, bat? This would be 0, right? Because there's no BB substring in this bad word. So this is how we can convert this bad word to some numbers and actually to vector. because if we find all substrings, then we can convert this this bat word to a vector. For example, if our substrings, right, or substrings would be BA, as we mentioned before, and BB, then what would be the expression or the features of this bat word? It will be 1, 0, right? What about BBT? I'm not sure if this is a valid word, but the features of this word would be 0 and 1, right? Because the BA is not contained in this word, but substring BB is contained in this word. So this is how we do this conversion, to convert to the substring to features. So to make it more like formal, like typically we can build a table, right? Here, for example, we use fixed length substrings, right? Our substring is always of the length 2, And here we have a list of 4 substrings: AR, AT, BA, and CA. And then we can convert each of our words to a features, right? For bar, it will be 1, 0, 1, 0, because AR is contained in bar, AT is not contained in bar, BA is contained in bar, and CA is not contained in bar. So this is how we do the conversion. But then let's think about what is computation cost of doing this. So obviously we need to do this conversion for all substrings right here. So this is definitely, the computation is definitely related to scaled with the number of substrings we have. So let's say number of S. And to actually find like whether the substring is contained in this word, we also need to iterate through all the letters in the word, right? We need to first find B, match B, and match A, and match R, right? So then computation cost is about number of substrings times the length of X, right? In this case, it will be 4 times 3, right? Because this is we have 4 substrings here, and we have all our words is in the length of 3, right? For example, R, right? This is a lot if we have a lot of substrings, right? Typically in the real world, we won't only have 4 substrings. We have so many substrings if we want to encode all the words we have here. In our vocabulary, we have a lot of it. For example, BB, BC, right? So this substrings, this computation cost is very high. Then here comes the kernel trick to reduce computation cost. And remember, there's one thing we can leverage here, that everything we need in the learning algorithm, such as perception, is dot product, right? So as we as we showed before, everything we need to compute is this facts times max in no matter learning or predicting problem. Then we apply kernel trick, right? We can reduce computation cost by only computing dot product. And we claim that if we want to compute the kernel, like the string kernel, the dot product for string kernel, we only need to do this. So basically, for each substring in X, we count how often it appears in Z, right? If we want to compute the dot product between 2 inputs, X and Z. For example, this X here, it may be a bar, right? And the Z here is probably bat. So why is this true? Because if you look closely, for bar and bat, their features, there are a lot of 0, right? For bar, there will be 0. For bat, it will be 0. Then when you compute the dot product between the two, compute the dot product between the two, you can just neglect all the 0 features in either of the word, right? So you can neglect this one because bar doesn't contain bat, and you can also neglect this one, CA, because both of them don't contain the substring. So this means that, and you can actually also neglect this this AR, right? Because it is not contained in BART, in BAT. This means that when you compute the dot product, you don't actually need to like iterate through all the substrings you have. You only need to iterate all the substrings content in one of the input, right? Let's say you just list all the substrings content in X, and then you count how often the substring appear in Z, right? So this is the trick here, and what would be the computation cost of this? So for each substring to iterate for each substring of X, this would of course require like the length of X, right? To iterate over them. And then for each substring, we count how often the substring appear in Z, right? This is can be done in Z time, the length of Z time by dynamic programming, right? So this can be done by dynamic programming, DP, right? So then our final computation cost is only, in this case, is only like length of X and length of Z, right? So this is much lower than the original cost. Original cost we need to it's scaled with the number of substrings, right? This is a very large if we have large vocabulary. But now this cost is not scaled with this number of substrings anymore. It's only scaled with the length of the input. This is more manageable because imagine like the longest English word we have in our dictionary is probably about 10, I guess. I'm not sure, probably about 20, yeah. But it's definitely not, there won't be as many like the letters in a word as the substrings in all the dictionary, yeah. So this is how we can reduce computing cost by using kernel trick for this string kernel example. Okay, that concludes this discussion, and thank you for listening.